Hello and welcome to Spring 2 Week 5 marking video for Year 10s. Remember, before you start, you need your green pen for writing in the correct answers. You need your blue pen for making annotations. Right, let's go. First one, the diagram shows a model of the particles in a gas and in a liquid. Here they are. Complete the diagram showing the arrangement of particles of the same substance in a solid. Okay, so this is what a solid looks like. What you need, two things to get your 2 marks for this question, very generous. One, you need to have your particles tightly packed together, so there should be no gaps between these particles that you're drawing. 2, they need to be in a regular arrangement. That means that they are in these lovely rows. If you've got those two things, you can have your 2 marks. The name of the process when a substance changes from a gas to a liquid. Okay, so changing between our 3 states, going from a solid to a liquid is melting, liquid to gas is boiling or evaporating, gas to liquid condensation, liquid to solid is freezing. We're going from a gas to a liquid, condensing. 1c, the substance in the diagram has a melting point of 98 degrees Celsius, a boiling point of 883 degrees Celsius. So whenever you get faced with a question about boiling melting points, just draw a little line and just note them onto yourself. So you've got this kind of setup where everything below the melting point is a solid, any temperature between the melting and boiling point is a liquid, and if it's over the boiling point, we know our substance is going to be a gas. It's asking the state of the substance at 20 degrees Celsius. So what you should then do is draw on the current temperature. So that's going to be here, less than 98. And that tells me it's below the melting point, so it is a solid. 1 mark for that tick. What type of change is a change of state? Tick 1 box. It's not a chemical, it's not a kinetic, it's not a permanent change. Of course we can change it back. So therefore it's a physical change. And just so we know, a physical change is a change where the chemical composition does not change. So for example, if you're melting an ice cube, you're going from water in a solid state to water in a liquid state, but it's still water, it's still H2O. The atoms haven't rearranged themselves, we haven't broken chemical bonds, made new chemical bonds. Okay, next up, which 2 statements are correct about the particles when a liquid turns into a gas? And I've just drawn that little diagram there just to help my memory. Tick 2 boxes. The particles become bigger. Note the particles are staying the same size. The particles are lighter. No, they have the same mass. The particles have more chemical energy. No, they wouldn't have more chemical energy either. We are adding energy in, and so they have more kinetic energy. They would start to be, therefore, moving faster. 2 marks there. As we go from a liquid to a gas, the particles are moving faster, they have more kinetic energy. Figure 2 shows a student making potato soup. There she is, putting the potatoes in the water. Lovely. The student places 0.5 kilograms of potato into a pan of water. During cooking, the temperature of the potato increases from 20 to 100 degrees Celsius. Specific heat capacity of a potato is 3,400 joules per kilogram degrees Celsius. Calculate the change in the thermal energy of the potato. As I realise it's a calculation question concerning specific heat capacity, I'm underlining my values and I'm bugging them. So M for mass, delta theta for the change in temperature, C for specific heat capacity. I'm trying to find out the change in the thermal energy. Using this equation, very generously have given you the equation here. Okay, so first of all I have listed my values and I've worked out that the change in temperature is 100 minus 20, which is 80 degrees Celsius. You get your first mark for being able to do that. 2, substitute in my values, so 0.5 times 3,400 times 80 is my second mark, and then working my answer out as 136,000 joules is my third mark there. 3 marks for that question. Okay, 2b. Why is the energy supplied by the cooker greater than that calculated in part A? So we calculated it to be 136,000, joules. It's saying that the cooker is supplying more energy than that. So if we think about our cooker and the heat, the thermal energy being supplied by the cooker on the hob, and here's my pan of potatoes boiling away, we're supplying energy to that water. However, lots of energy is also being lost to the surroundings, and of course we've used the term not lost to the surroundings but being dissipated to the surroundings. So the cooker's putting in all this energy Not all of it's going to heating up the water. Some of it is being dissipated to the surroundings. 1 mark. One way that a student could reduce the time to heat the potato to 100 degrees Celsius. So in simple terms, how could you speed up the time it takes to heat up the water? Well, one thing you could do, you've probably done this at home when you're cooking, is put a lid on the saucepan. Or 2, you could turn up the cooker. Of course, doing it this way is going to waste more energy, more is going to be dissipated to the surroundings. This one would be the better one to do. Save on your energy bills. Figure 2 shows a food processor. Here it is. So we'll put our food in here, and the blades whirl around and blend up the food, make a nice smooth soup. The jug is made of plastic with low thermal conductivity, so I'm thinking that this is a thermal insulator. It's very difficult for the thermal energy to pass through this plastic here. Why is this an advantage? Think about why would we make this food processor out of plastic? First mark is saying that there would be a lower rate of energy transfer. So that means the energy is going to move through the plastic slower than if it was made of something like a metal. 2, one thing about why is this an advantage? This will mean that the soup will remain at a higher temperature for longer. So your soup is going to remain hotter, which is what you want. You don't want cold soup. 2 marks there. Okay, figure 3 shows a kettle a student used to determine the specific heat capacity of water. There it is. Student placed different masses of water into the kettle and timed how long it took for the water to reach the boiling point. Right, little question as a little hint here. At what temperature did the student stop timing? So at a temperature which you're going to stop, well, it says they're going to time how long it took for the water to reach the boiling point. So I know they're going to stop boiling at 100 degrees Celsius. That's the boiling point of water. So timing from when it starts to when the water reaches 100 degrees Celsius. And of course the student carried out the experiment 3 times, and the results are shown in the table below. So here we can see they're working out the mass of the water, their timing for the time it takes for the water to boil, and they're doing that 3 times and calculating a mean. They've also done here mass times change in temperature for some reason, we're going to talk about it in a second, and they've got their results for the amount of energy being supplied in kilojoules here. Another little question as a hint. Why did the students start to calculate mass times change in temperature? If you think about this question, they were originally trying to work out the specific heat capacity of water, and if we think about a specific heat capacity formula, it's delta E equals, I'm going to write it slightly different, C, specific heat capacity, multiplied by the mass, multiplied by delta theta, which is the change in the temperature. So this part here, they're already working out for themselves, and they've also got the energy supplied here. This is going to allow them later on to a bit easier be able to work out the change, be able to work out the specific heat capacity, C. So they're just making that bit easier for themselves already by putting it in their results table. Okay, suggest how the student was able to ensure that the change in temperature was the same for each mass of water. So think about the change in temperature is the final temperature minus the start temperature. And if they want to keep the change in the temperature the same, they need to control both of these. They need to keep both of these the same. So if you're 2 marks, you need to say how they're keeping the final temperature the same, how they're keeping the start temperature the same, to overall keep the change in temperature the same. So first one is a little bit easier because water always boils at the same temperature. So that's going to be their final temperature. They're keeping the same. So it's always going to be 100 degrees Celsius when they'll start timing. The start temperature, to make sure that's the same, they need to allow enough time for water to cool at the start to room temperature. Okay, so don't want to put hot water in the kettle one time and cold water in the kettle another time. They're just going to make sure it's at room temperature each time, maybe around about 20 degrees Celsius, and then they'll start their experiment. 2 marks there. 3b. Calculate the uncertainty in the student's measurements of time to boil when the mass of water was 1.75 kilograms. Okay, here's our results for 1.75 kilograms. 298 seconds, 300 seconds, 302 seconds. They haven't worked out the mean yet or the energy supplied. Little hint, how to calculate uncertainty. First you calculate the mean of those times. So 298, 300, 302. That's what we need to do first, and I've done it here. So we do 298 plus 300 plus 302 divided by 3 is 300. Next thing, find the range of times. So the range is the largest minus the smallest, so that's 302 minus 298, the range is 4. Okay, to work out the uncertainty, you're thinking about the uncertainty in terms of the measurement. Okay, so how much either side basically could this number possibly be wrong? So we do, uncertainty is the mean plus or minus the range divided by 2. So think about the amount either side. So it's 900 plus or minus 2 seconds is 300 plus or minus 2 seconds is the uncertainty either side of that measurement where it could be a little bit different. So 300 plus or minus 2 seconds for your 2 marks. Okay, 3C, the power rated of the kettle is 2.2 kilowatts. Calculate the average electrical energy used by the kettle in kilojoules for 1.75 kilograms to reach boiling point. So first of all, as usual, I'm listing my values. Don't know the energy in kilojoules, that's what the question wanted it in. It's telling me that the power is 2.2 kilowatts. I know from my last question I worked out that the mean time was 300 seconds. We need to convert it to standard units, so I'm going to multiply by 1,000 to get it into 2,200 watts. I then state my formula, which is energy equals power times time. Energy equals 2,200 times 300, so energy comes out at 660,000 joules. But then the question wants it in kilojoules, so I need to convert it back to 660 kilojoules. 2 marks there. 3D. The student plotted a graph of energy supplied in kilojoules against mass times change in temperature in kilograms degrees Celsius. And the figure 4 is showing the graph for the ones they've plotted, and it's asking us to plot the final missing points and to draw a line of best fit on the graph. And you've got a little hint there that the line shouldn't go through the origin. So looking back at our table, we want to plot the mass times change in the temperature. This is going to be on the x-axis against the energy supplied in kilojoules on the y-axis. We now know this number. We worked it out in our power question here to be 660. So I can plot these results using my pencil, using small crosses. You get 1 mark for accurately plotting your points, another mark for drawing a nice straight line of best fit through these points. Okay, so 2 marks for a graph that looks just like mine. It's then asking us to use the graph to determine the mean value of the specific heat capacity of water for the student's investigation. Okay, over here I've written the specific heat capacity formula. So I've written delta E equals, I've written it a little bit different to how I've learnt it, C times M times delta theta. If you think that you're trying to work out the specific heat capacity, I've just rearranged that. So I've divided both sides by M times delta theta. Specific heat capacity is the change in the energy divided by mass times delta theta. And if we think about this here, change in energy here is on my y-axis, mass times change in temperature in kilograms degrees Celsius is on my x-axis. So I'm looking at y divided by x. So the specific heat capacity is the gradient of this line. So to work out my gradient, I need to first of all pick 2 points that I'm going to use. So I'm going to be looking for points that go through where my grid lines intersect each other. So I think 1 point here looks good, and I'm going to go for this point here as well, is where some grid lines are intersecting. So this one here is 80, 400. This one here is 40, 220. Okay, and I can draw my little right angle triangle, and I can begin to work out my gradient. So the 2 points I've chosen are 80, 400 and 40, 220. Now, this is a really tricky point. Well done if you picked up on this. To work out specific heat capacity, my specific heat capacity is going to be in joules per kilogram degrees Celsius. Take a note here, joules. This here is in kilojoules, so what I need to do before I start is convert these into joules. Okay, so I'm going to multiply these values by 1,000. These are the ones that are the energy supplied, the change in energy. So it's actually 80, 400,000, 40, 220,000. Okay, so now I need to work out my gradient. So as we should know, gradient equals the change in the y over the change in the x, or we could say rise over run. So changing the y, I'm going to do 400,000 minus 220,000. Divide that by 80 minus 40. So always double check on my calculator, even with most simple calculations, because we're allowed one in our science GCSE. Changing y comes out at 180,000. 80 minus 40, I'm going to do that one in my head, is 40. So I can do 180,000 divided by 40, comes out at 4,500, and my units joules per kilogram degrees Celsius. Now, your line might be slightly different to mine, how you've drawn it in terms of its gradient. You're allowed here any number between 4,200 to 4,800. So if you've got a number anywhere in that range, you can give yourself 3 marks there. Well done if you got that question. Really tricky. Okay, last question we're going to have a look at. The student's value for the specific heat capacity of water was greater than the accepted value. Suggest why. So they're saying that this value they've worked out here is actually greater than what water actually is. Why might that be? This is because some of the energy that gets put into heating up the water does not actually raise the temperature of the water. Some of it, for example, might be put into, might be dissipated to surroundings, and that causes the specific heat capacity value to seem higher than it is. It seems like you need to put in more energy to raise up that water than is actually required. Okay, once you finish marking that exam, make sure you give yourself on the front a mark at 28, and we're done.